Welcome everybody to my talk about in-memory apps with EclipseStore. My name is Florian. I'm one of the co-founders of the company behind the project. First of all, the legal stuff. So let's see what we will pack in the next minutes. First of all, the rationale, the idea behind the project, how we came up with it, what's the reason behind it. Then we'll go directly into using it. First of all, of course, the installation, how to start it up, configure it. Then what about loading data, and of course storing data. Then we'll dive a bit deeper, how to customize the engine, for example, custom type handlers, or what do we do when classes change, class evolution over the runtime of a project. Some backup and housekeeping, how the engine works internally, to get a look behind the scenes. And last but not least, the migration from MicroStream to EclipseStore. For history reasons, the project was called MicroStream before, like the company, but then we moved it over to the Eclipse Foundation. Now there are two projects. The first one is the Eclipse serializer, which takes care of creating bytes out of objects and vice versa. And on top of it is the storage engine called EclipseStore. So if you developed applications before with MicroStream, we have an automated migration to EclipseStore, because where the active development happens now at the Eclipse Foundation. The MicroStream framework itself will receive security updates until the end of the year. But if you want to dive in the project, just start with EclipseStore, and this is the active development branch. All right, so if you look at the current state of application development, especially if a database is involved, we will see major drawbacks we have to deal with. In Java itself, we have our object model, which is a perfect multi-model data structure in itself. We can have key values in maps, we have lists, and can design the pointers like we want. But in a databases or data storages, there are different schemas, like tables or graphs, which are incompatible with the Java graph itself. We have event streaming software, and so on and so on. But the problem stays the same all the time. We have to deal with two different data models or schemas. And in order to get it to work, we have to adapt our Java classes to a mostly strongly limited form. And in between, a highly complex mapping framework is needed. Most of the time, of course, JPA and Hibernate, or different other mapping frameworks, and this results in a tremendous loss of performance, actually. The database itself is mostly quite quick to get the data, but then we have to convert all the data into our objects to create Java objects, and this process is expensive. And every single time you query the data from your data source, even if it comes from the cache, the objects have to be created every single time, and this is expensive. And on top of that, of course, you need mostly some query language to get the data, or a Java Query API, or some frameworks like Spring Data and so on. And all in all, with caching in between and connection pooling and whatnot, it's a complex architecture and an infamous source of error. And you need experienced specialists for these frameworks most of the time. And this is a high effort and cost for the entire database development process and maintenance, of course. So that's where the idea for the EclipseStore framework kicked in. So we said, we have the perfect data structure anyway in Java, why we don't use it? The only thing which is missing in a JVM is how we could store data. The JVM or all the Java frameworks itself deliver us with all the features we need. We can do validation, we can do user management, and so on and so on. There's everything there in Java, except persistence. So we thought we tackled that problem, and we came up with this idea. EclipseStore is a unique storage technology which you can't really compare with different other database solutions out there, which stores the object graphs natively, like the JVM does on a heap. And this can be done without an expensive transformation or an incompatible data structure on the other side, because we store the data into binary format, how the JVM keeps it on a heap. So no conversion is needed. And this is the key difference to all database systems, and it provides fantastic benefits if you look at it. It feels like a native Java function for just storing data. Only one object model or schema is needed, so no transformation anymore, and therefore no more loss of performance through a mapping or mapping process. And this makes an in-memory computing paradigm possible in Java. And you can max out all the performance benefits of the JVM, like the JIT compiler or all the new performance enhancements of the new Java versions, like the zero-JIT garbage collector and so on. Every time the JVM has performance updates, you will benefit from it, of course, and to a much more simple architecture. And this can speed up the development process as well, so your time to market. But if you develop this way, it's a paradigm change. Before, the database was the source of truth, and your application only received copies of the data. Every query led to a copy of the data in the database. Now, with this approach, the source of truth is the application itself. And with EclipseStore, you just persist the data to a binary form on your hard disk or to a blob store in the cloud. But the application now is the source of truth and the boss of all things. And you don't get object copies from the database. You're working on a shared object graph for all users, for all sessions, for all threads. And that's the one thing you have to keep in mind. All right. So EclipseStore itself is not an external server process you're talking to, but just a simple Java library which you bring into your project by adding a dependency. So current version is 1.3.2, and it's available in Maven Central. And of course, since we are part of the Eclipse Foundation, the software is available under the Eclipse license, the Eclipse open source license. Yeah. Of course, you don't have to use Maven, just a build tool of your choice. Bring it into your project, and you can get started. So let's see. This is the most simple form to initialize the engine. The embedded storage manager is the connector between the object graph on the heap and the storage layer, the binary layer. Most simple way to start it up with the default configuration is the embedded storage.start. And to end the lifecycle, you call the shutdown. So what happens on start? The engine will check if there's an existing storage lying around on your hard disk or wherever. And if there is data existent, it will restore the objects on the heap automatically. So, but don't worry, the engine won't restore all the objects which are in the storage, but only these ones which are defined as eager loaded. So you can add lazy loading points inside of your data model, and then the lazy loading will happen on demand, only when you're accessing these objects. All the other stuff is by default eager, meaning every single object which are reachable from the root object on will be loaded and pumped or restored in the memory. The root object itself is the entry point of the persistent object graph, which can be connected to the storage manager, and all object which is reachable from there can be persisted and restored at any point in time. So, like you see, the storage manager is mostly created with the factory methods of the embedded storage class, with the most common settings like the database directory or and the root instance. But for more complex configurations, we have several other ways. For example, the embedded storage foundation. The embedded storage foundation is the most low-level way to configure the engine. It's basically the collection of all the engine's parts from where the storage manager will be constructed later on. And the API, or the framework, is a strictly interface-based architecture, meaning you can, or you could, if you like, exchange or re-implement every single aspect of the engine, and so forth. It's highly configurable. So the embedded storage foundation is a builder pattern style configuration where all the aspects can be customized. And yeah, like I said, it's the most low-level way of configuring things. If you bring in the configuration dependency, it's a more higher level property-based configuration API, and it supports external configuration as well. So you just have to call off your setters. Maybe you want to change the backup directory or up the channel count. The channel count is just more parallel I/O operations. So if you use 4 channels, for example, the I/O handler will run 4 threads on 4 different parts of your binary target. On the hard disk, it would be 4 different directories or 4 different buckets in S3, for example. So, and this configuration type consolidates the most widely used parameters from the foundation in one place, and its output, again, is a storage foundation from where a storage manager can be created again. And it can access external configuration like XML, YAML, property files, whatever you like, and therefore we provide load methods for that. If you want to create more profiles like a configuration for dev, prod, test, and so on. And the framework comes with several integrations and different other frameworks like Spring Boot or common CDI integration. Other framework vendors provide integrations by themselves, like Micronaut and the Helidon guys provide EclipseStore integrations, and therefore you could use the configuration layer of the framework itself, for example, the application YAML from Spring Boot, put the properties there, and EclipseStore will read the properties from the framework's configuration. All right. So, what about loading data? Like I said, it can be done in 2 ways, eager and lazy. And by default, everything in your object graph will be loaded eagerly, except you define lazy loading points. So this means if nothing is defined as lazy, all the objects, all the complete graph will be loaded immediately. Of course, this makes sense for smaller amounts of data, maybe for embedded applications or mobile devices or so, but in the most common proper applications, you will leverage the lazy loading, of course. So I showed the root object, meaning the entry point of the object graph. This can be accessed by the root method. And in this simple example, we'll just check if there is any root, meaning there is an existing storage. Otherwise, we'll create a default root, store it, and go from there. This will happen on the first startup only, of course, because at the second startup, the root will be there in the storage and will be automatically restored. So this is one way to initialize your database with default values. So how do we do lazy loading? Given this simple application, a business application with business years, and this approach could be a problem. So during initialization, the root instance would be loaded from there. It's a hash map with all the business year instances with a list and all turnovers. So let's say for 20 years, 1 million sales per year would be 20 million sales entities or turnover entities. And this could be a problem because all of the sales entities would be pumped into the RAM directly at the startup. And we don't want that. Most of the time, you only need the turnovers of the current year to work with. All the stuff is archive data. So we want to load this stuff lazily. So how do we do that? Would be nice if you just add, say, lazy, and that's exactly how it's done. You wrap the stuff you want to load lazy in a lazy wrapper type, and this is all you have to do to define the lazy loading points in your application. So a lot of people ask us, so why don't you use an annotation? Why does it have to be a concrete type? I will tell you later what the reason was for that. So how do we access the content of this lazy reference? It's just a simple getter. Turnover lazy wraps the actual list, the actual data in it, and the get method will check if it's on a heap. If not, it will recreate this subgraph from the storage, merge it into the live shared object graph, and it will go from there. And the get call reloads all the data as needed, so you don't have to mess around with select blah from turnovers where ID is something. That's all done by the engine in the background. You don't need a query language anymore of some sort. And this is possible because the serializer in the background, in combination with the storage engine, has an internal object ID mapping, meaning this technique is called swizzling, actually on Wikipedia. Didn't know that before. The engine itself maps every single object internally to a unique ID, just a long value. And this long value basically is the reference to the pointer on a heap, and therefore we are able to restore the object graph and keep the referential integrity all the time. And that's why we can lazy load parts of the objects and merge it back into the live graph and unload it and reload it at any given point in time. So, and that's also why you don't need any technical IDs. So there is no primary or foreign key anymore. You just have your Java pointers, and the engine will work with them. Of course, you can have object IDs which are business relevant, like a customer number or an ISBN in a book or so, but no more technical IDs are needed. The technical ID is the pointer itself. So there are several methods to initialize a lazy reference. Just call the lazy reference factory method and hand over the actual instance which you want to wrap. Just a null can be wrapped as well, or you initialize it with null itself. Doesn't matter. So, like I said, a lot of people ask us, why don't you use an annotation? Why do we use an actual wrapper type, which pollutes the class model, some would say? Now, first of all, we don't do any bytecode manipulation at runtime. So if you wanted to interfere with the recreation of the object recreation, we have to put some intermediate stuff in there. So, and if we would have used an annotation, we only had the possibility with bytecode manipulation or aspect-oriented stuff or anything like that. And the next reason was the annotations are limited only on field level. You can put an annotation, but we wanted to be able to create a lazy declaration inside generics as well. And this couldn't be done with annotations. But if we, in this example, wanted only to lazy load the value of the map, this can only be done with concrete types, not annotations. So these are the two key points why we decided to create a lazy type, not a lazy annotation. Yeah, and if we would have used bytecode manipulation, this interferes with debuggability, the runtime behavior, and so on. And this was all stuff we didn't want to pollute the application with, to make things harder. So it's the more convenient way for development and runtime purposes. All right, so if we use the lazy loading, this is an internal technical detail of the business object, so we want to hide it, of course. So the getter won't return a lazy list, but the list itself, and therefore we just check if the lazy is null. Otherwise, we'll return its contents. This looks a bit inconvenient, so therefore we just created a convenient method, just called lazy get, and hand over the field, and the null check is done internally. So it's a short way to unwrap a lazy reference and reload it on demand. Just call lazy get, a static one, hand over the lazy reference, and all the checks are done internally. And the optional would be an alternative as well, of course. So the class basically would look like this. What parts of it? You have a lazy field. The getter unwraps the lazy one, and the setter creates just a new lazy reference for the internal field. And so you can hide the lazy detail from the caller. It's just a technical detail which you keep inside of your implementation. And this is the only thing which pollutes your business model, your approaches. From a technical perspective, all the other approaches can be just used as is. You could design your approaches without implementing serializable, without any other special interface or superclass, or even without annotations of some sort, just using as they are. You can even use all external types or all JDK types, all collections, all date types. You bring in different frameworks like the Money API, for example, and EclipseStore will happily persist them or work with them. So there is no limit for using types or designing an object model. So some more lazy methods which come in handy. Of course, the getter will load the stuff on demand. The lazy peek will just return the actual state. So if the lazy reference isn't loaded, it will return null. And the lazy clear will remove the objects from the heap, and they can be restored later from the binary area, from the binary storage. So the lazy clear frees up heap memory, which could be essential over the runtime of the application, because most of the time, of course, you will have a lot of more data than you have RAM available. So you have to keep the RAM clear. So you have to unload lazy references, but not by hand all the time, of course. For that, we have a lazy reference manager running in the background, which checks by default with a memory quota and a timeout, which lazy references are least used, and cleans them up first and keeps the hot data in memory. So the most touched lazy references will stay on a heap, and the other stuff will be cleared out. And the more full the RAM gets, the more aggressively the reference manager will clear the memory up, so you don't run into out-of-memory problems or heap overflow problems. Yeah. So that's all you need to know basically about loading data. You can define lazy loading points. Lazy handling is done in the background, or the memory cleanup, and all the other stuff will be loaded eagerly, meaning it's available from the startup on your heap. Okay. So, what about storing data? The engine itself won't recognize changes automatically because we don't have a comparison of the older and the newer state. So you have to tell the engine what's changed over the time. And one rule of thumb is store the modified object, and that's it. And a store operation is an atomic operation. So it's not, it's an internal transaction with strong consistency. So, and the only thing, of course, you have to keep in mind what object has actually changed. For example, if you set the root, there's a convenience method for it, just store the root. Probably only once if you provide an initial data. If you change an entity, let's say we update the name of a company, of a customer, of course we store the customer. So, and if we add an item to a list, the actually modified object is the list itself. So we have to store the list. Same applies, of course, if you remove stuff from the list or swap stuff out. But don't worry, let's say we have 1 million entities in a list and we add another one and we store the list. Not the whole list will be written out again, but only the new object. Because EclipseStore stores only the deltas in a model. So if you have multiple changes at once, bug updates or whatever, there are store all methods. So you can put multiple changes into one transaction in one I/O operation. Because every store, of course, initializes an I/O operation, and this is the expensive stuff. So you want to keep it to a minimum. So every time you have a chance to combine store operations, you can do it with a store all method. Okay, so this store method I showed you, the store all or the store before, this is just a shortcut for this one. The storage manager can create a storer. The storer itself is basically the same as a transaction object. Then you can register changed values, changed references, and in the end you call a commit. This is what happens if you call the store method of the embedded storage manager. Most of the time it will be enough. You can utilize the store all method if you have multiple objects, but if you want to span a transaction over a longer time, we recommend just to create a storer, register all the changes in the storer, and in the end call the commit. By default, the lazy storer is used, meaning this is the default storing mode. Referenced instances are stored only if they have not been stored yet. If a reference instance has been stored previously, it is not stored again, even if it has been modified. So meaning, if you call store on a customer, the customer will be stored anyway, but all referenced objects from there are only stored if they are new. So if you're not sure in your code what's actually changed further down the graph, which is rarely the case, but sometimes maybe, you can use an eager storer. The eager storer stores everything anew from this pointer on. So the whole subgraph will be written anew, and you can go absolutely sure that every single changed byte will be written in a storage again. So of course, this is a more expensive operation because the graph can be bigger. So for the transaction payload will be bigger, and so that's a trade-off. But like I said, in a project, you mostly know which objects are changed because you see the code. Just store these objects, and you're good to go. So different way to configure storing is a field evaluator. By default, the lazy storer stores only the new reference stuff, or you could manipulate the field evaluation by a simple lambda, which can be registered in the foundation types. For example, you create an eager annotation, write them over all fields which should be stored always eagerly, register the evaluator, and so you can define always eagerly stored fields, for example, if you have compound types or depending on your object model. This is one way to configure the storing behavior. So in short, the default store methods are lazy by default, like the lazy storer, which leverages the field evaluator, which does by default nothing, but you could change the behavior, or you create an eager storer and store everything anew. What if you want to leave out fields like computed fields, temporary flags, and so on? We decided to use the default JDK keyword transient by default. So every transient field isn't part of the persistent object graph and won't be restored again. So this comes in handy if you have temporary stuff in your class and want to leave them out of the persistent graph. Of course, this can be customized as well. If you have already existing data model where all the temporary flags, let's say, start with an underscore, you could use another evaluator and say it's only stored if the field doesn't start with an underscore. So this can be customized as well for existing code bases. It could come in handy. Yeah, and basically that's everything you need to know about storing data. Just a simple store method, store what you've changed, and you're good to go. So what about deleting data? In a database, of course, you fire up a delete from something query with a condition, and the data is removed from the database. So, but how do we delete data in Java? Objects are removed by the garbage collector if they are not reachable anymore by any pointer. That's when you delete objects. Let's say the item only is referenced by the list, and if you remove the item from the list and store the list, the item will vanish eventually. It will be removed from the heap, from the garbage collector by the JDK garbage collector. So, but what about the storage? Will it stay there forever? That's what we thought. So we had to re-implement a garbage collector on a storage layer, which is part of our housekeeping process, which keeps all the files tidy and defragments them, as well as all the dereferenced objects will be removed from the storage eventually by our garbage collector on the storage level. All right, so don't worry about polluting your storage with dereferenced objects. Our housekeeping will take care of that. Just remove the objects from your graph, and they will vanish eventually. So this is CRUD with EclipseStore. The loading is done eagerly, otherwise you have to define them lazy. Storing is just a simple store method, and deleting will happen like on the JVM itself. All right, so these are the basics of the storage engine: how to manage and graph, how to keep it persistent, how to restore it in memory. And now let's look a bit into customization. What can we customize? How can we optimize the engine, get up my performance, less memory consumption, and so on? And that can be done basically with custom type handlers. A type handler is the type which is used to create the binary representation out of an object, and vice versa. So basically the serialization implementation for a certain type. In EclipseStore, we don't depend on the JDK API for serialization, so no IO serializable and so on. But we use external type handlers. That's what a type handler in EclipseStore is. You can register a type handler which is used for a certain type in the engine itself. So you can customize the type handling for types where you don't own the code as well. So let's say you want to customize the type handling for the local date. You just register the type handler and it will be used for a certain type. For example, the given class time slot, we have a primitive slot number and two references, a start and end object. EclipseStore comes with a lot of predefined type handlers, for example, for collection types, date types, or most common use types in the JDK. But for custom purchase, we have to create generic ones. And the generic type handler only inlines the primitive values in the record, in a binary record, and every single reference will be a new record in a storage. And we have to do that to keep the referential integrity intact. But if you don't need a referential integrity, but equality is enough, you can inline, for example, here the local date times, start and end, in a single record which reduces the amount of bytes written to the binary layer immensely, and of course it will reduce the memory consumption. So the default generically created handler would create a time slot. It creates this object ID. Then there's a special type ID, and then the data. The first one would be the primitive slot number. It's inlined, and the other two are pointers, object IDs again for the two date times, which will be referenced. So it creates 3 records, 1 per reference, 1 per object. But what we want is, we want to inline these 2 timestamp values of the local date times into the time slot record, and therefore boost the performance and reduce memory consumption. There are 2 ways to create custom type handlers. The first one would be the easy one. Yeah, it's big enough. So just create a static method in your code, which returns a type handler, and this will be used by the engine. Then we have factory methods where you basically say how a field is written, how a field is read. And of course, this can only be done if you own the code. If you want to customize external types from third-party libraries or from the JDK, you just create an instance or a special class, for example, for a buffered image, which will be encoded as a PNG into the storage, and then register this type in a foundation, and it will be used for buffered images. And this is how you can customize the binary representation of objects and optimize it to your needs. All right, so what will happen when my classes change? And they will. There's always a version 2. The engine can handle changes of any sort. If you rename classes, add fields, remove fields, refactor packages, and so on, it's done by a custom type mapping, or we call it legacy type mapping, and it doesn't matter how many version evolutions the object undergoes, the engine will apply an automatically created mapping if it's possible. For example, primitive type conversion from int to long, it can be done without a loss, But if you, let's say, split the name into first and last name, the engine can't do it automatically, so it can provide a custom type mapping for that and control how the fields or the data will evolve over class changes. So, and this is done on demand only, so only if this object is loaded from the memory, from the binary layer to the memory, the conversion will take place. So there is no need to rewrite the whole storage every time you change a class, but only on demand. This would be the default console output when the engine detects a type change. So it says, oh, in my storage there's an older version compared to the class on the class path, so we have to do a mapping. And you can provide a type mapping either by a text file or by an API, where you can define all the changes, all the renames, and so on. So this can be handled by the engine without problems. So. And of course, backup is an important part. We provide continuous backup. This is just simply configured by providing a backup directory. You can use a different binary target as well. Let's say your live data is on a disk and your backup will be written to a bucket in the cloud. Just define a different backup file system and use this one. And the continuous backup will be written parallel to the live storage, and as well as a full backup, which is basically a snapshot of the storage, which can be written to a different file system as well. So let's look what's done in the housekeeping I mentioned. The housekeeping is a process which runs in the background in parallel and accesses your storage and keeps your storage files clean. It can be configured how many time it has or the time budget it gets. So for write-heavy operations, we recommend to up the budget for the housekeeping, that the files could be kept clean. This has to be done because we only append stuff to the file storage. We never modify the files. We have to do this because certain storage targets won't allow modifying the blobs, like the S3, for example. The blobs are immutable, so we can only append stuff, and therefore we have to do a defragmentation or a cleanup of the files, because sometimes, of course, bytes in the files become irrelevant, old data, newly written. If you overwrite stuff or if you delete stuff, some bytes can be cleaned up, and that's what the housekeeping does. Of course, a cache cleanup, because we have a binary cache on the client side. And the garbage collection itself is part of the housekeeping as well, which detects unreachable objects and marks them as deletable. So, like the JVM garbage collector. And this is all part of the housekeeping. Can configure the interval and time budget. Like I said, for write-heavy operations, we recommend to increase this one. But most of the time, it's not really necessary, because the housekeeping itself is adaptive, meaning when the garbage collector won't reach the cleanup phase, the housekeeping itself will give it a bit more time and a bit more until the garbage collector does its job. And therefore, only for really write-heavy stuff, you should increase these values. All the housekeeping operations can be called manually again. For example, in cron jobs, you say every night at 3 o'clock, we'll do a full file sweep, a full garbage collection, clean up the storage. Therefore, this method can be called from the embedded storage manager itself. All right, so if you want to migrate from MicroStream to EclipseStore, that's a link for the tool, which uses Open Rewrite under the hood and modifies your code base as well as the storage. And then you can migrate from all the MicroStream projects to EclipseStore. The link is also in the documentation, so you don't have to remember it. And that's basically it. So let's see what's coming up in the future. One of the most exciting features I like to talk is a concept called GigaMap. It's an index collection designed to cope with vast amounts of data. It stores all the data internally in nested, lazily loaded segments, and these are backed by indices, meaning this allows for efficient querying of data without the need to load it all into memory. Because currently, if you want to filter data from a collection, for example, it has to be on a heap. So if you have, let's say, 50 million entities in a list, you want to filter them, you have to load them in a heap, on a heap. Then you use Java streams, filter them, and go from there. This can be a problem if you have really huge data or you don't segment your data properly with maps, for example. And therefore, we came up with a GigaMap, which uses a client-side index, or indices, which lie off-heap. And the index is queried off-heap, and only the needed segments of the result will be loaded on the heap. And this is the fastest way possible to query the data on a JVM and just load the stuff under the hood lazy. So you don't need to define lazy loading points in your application. It's done by the GigaMap under the hood automatically. So, and it doesn't have the limit of the Java util collections. They use an integer as an array index. The GigaMap doesn't, so we have the possibility to store up to 2 to the power of 50 elements. So that should be enough for every use case, I guess. And this is, yeah, this makes this collection a highly efficient and flexible solution for managing, querying, and storing large quantities of data easily with our storage approach. All the queries and indices are defined with a Java API as well, so there's no need to learn another query language. It's all done with Java, and the result set itself will be iterable or streamable, so you can page the results on demand. This is not available yet. The public beta will start soon. So if you just subscribe to one of our channels, newsletter, Twitter, whatever, we'll inform when the public beta starts. So there are some useful links, of course, our website, the documentation, the project site of the Eclipse Foundation, and our GitHub repository. And a lookout for the next events. We provide, the JAVAPRO provides EclipseStore training for free. The dates are available at the JAVAPRO website. And we have starter days coming up in several locations with a getting started guide, live coding, and so on if you're interested. These are on the starter day website. All right. So thanks for listening. If you have any questions. Yeah, just wanna. Okay, so. So can I use it as an in-memory graph database to replace Neo4j? Exactly. Your application effectively becomes the database, and EclipseStore is a way of persisting the data. So it can be, it is an in-memory database approach. Yeah. So you can replace Neo4j. Yeah. Yeah. For the cluster. The stuff I showed you was the open source part, which is a single JVM approach, meaning one JVM accesses one storage. If you want to scale horizontally, we have an enterprise stack built on top of it. We provide it as a service and for on-prem, but the programming doesn't differ from a single JVM node. The only thing you have to change, you don't use an embedded storage manager, you use a cluster storage manager, which implements the same interface, so the rest of your code base stays exactly as is. The only thing you have to exchange is the storage manager implementation. The rest is the same. Yeah. Oh, good question. The lazy stored data could be streamed. Yeah, this is done by the gigamap. The gigamap queries an index and streams the result set in the memory. And if you stop streaming, no more data is pumped into the on a heap. But with the current lazy loading, if you call the getter of the lazy reference, all objects which are referenced by this lazy reference are loaded into the RAM, of course, until the next lazy references are reached. So a lazy get is a swapping operation into the memory, or a mapping operation, but it's not streamable. Yeah. Yeah, this would be great, of course, if EclipseStore would be part of the JVM. We actually talked about these ideas with the JDK guys. We'll see. Yeah. Yeah. Good point. So, concurrency. We are operating on a single shared object graph, no more copies. So we have to worry about concurrency. Concurrent access has to be managed. Either with JDK core stuff, you can synchronize with the most simple method, but it makes your application effectively single-threaded. So different way would be to use reentrant logs. So read access or read operations would run in parallel, only the write operations log hard. We provide a convenient API for that in our Spring Boot application. In Spring Boot, we can use aspect-oriented stuff. So it's only necessary to define read and write operations. You just write an add write or an add read over a method, and the logging will be done by the Spring Boot integration, for example. So there are several ways, of course, to handle concurrency in Java or in our integrations, but you have to do it. Yeah. Yeah, if the root will be stored with the lazy storer, only the new stuff will be written. If you use an eager storer, everything will be written. That's the difference. We don't have the possibility to compare two states. We only have one state on a heap. So you have to decide if you want to do lazy or eager storing. Yeah. OpenG9, yeah, it's actually one of the best performing VMs we've tested because of its unique memory layout. We run tests against basically every relevant JDK out there from version 8 to the current one. And yeah, OpenG9 was one of the fastest. Yeah, that's a good question. The measurements we've done with the gigamap, the index queries happen in microseconds. Doesn't really matter how big the data is. The index lies off heap and can be accessed in the most fast or in the fastest way possible on a memory. So you don't have to worry about the size which lies in a gigamap. The query will always happen on heap. So it's way faster than everything else. The only thing which can be slow if the result set contains millions or billions of data and you load it all at once. Therefore, the result sets are streamable or pageable, and you can load them bit by bit. Yeah. But the queries are very, very fast. Yeah. Yeah, 1000x faster. Yeah, it depends on a use case. But the comparison is a bit difficult because our queries always happen on a heap. If you query a database, you have I/O in between. But we did comparisons. The application where the comparisons are done is open source. It's on GitHub. You can fire it up, exchange the database you like, put the cache in between, and you will see the actual performance differences. Sometimes the database is as fast as EclipseStore. Sometimes we are 1,000x faster, depending on use case. But this is the factor you can reach. So we don't talk about 10% faster or 20% faster in the long run, but multiple 10x faster than a database. Yeah, sounds to be good to be true. The thing you have to keep in mind, it's a paradigm change. You have to rethink. Most of the people think in databases, external process, they are used to it, the team is used to it. It's a new approach. So you have to try it out by yourself, see how your team adapts to it, but you have a lot of pros, so it's worth a look, I'd say. The only con I really see for me is you have to handle concurrency on a heap in your software. But this is a price I'm willing to pay for all the good stuff I get out of it. Yeah. All right. Thanks for listening. See you next year.